Okay, well here we are in Chapter 6 of Elementary Statistics. We're going to talk about the normal distribution. I've noticed that Miss O'Brien's notes, as I looked at them, are very good. Her PowerPoints are very good. These are very similar. This is a PowerPoint that's produced by your book publisher, and I'm voicing over it. So I don't know that I'm going to help you a great deal more than what you've already got in your toolbox on Blackboard, but we'll sure sometimes just saying things a different way helps. So this is again the normal distribution. We're going to start with just 6.1 with this video, then I'll do another one for 6.2 and 6.3 and 6.4. So there'll be 4 videos that'll be posted along with her videos in the notes. The objectives, we're going to talk not so much about distributions as symmetric or skewed, but we're going to talk about the properties of a normal distribution. That's something I'm going to want you to know for a quiz. You're going to have to find the area under the standard normal distribution given z-values, and then we'll start talking about probabilities for normally distributed variable. So we're going to, again, probably just do 1 through 3 in this first section. Many continuous variables have distributions that are bell-shaped and are called approximately normally distributed variables. We call it, you've heard probably if you've been around, that talk about things fitting the typical bell curve or the Gaussian distribution. You know, things like height. If you had a curve and you were going to come down here and draw a curve for height, well, you'd come along here, and most people are probably about this height, and then you get those that are really tall over here and really short over here. And so the curve, though, where most of your people fall right in here, that's a bell curve. This shape is a bell curve or a Gaussian distribution. The mathematical equation for the normal distribution looks like this. E is a number. Pi, of course, is 3.14 or about that. Mu is the population mean, and sigma is the population standard deviation. I'm not going to ask you to know this equation, so don't panic over it. It's okay. It's there because that's how this is calculated. All right, the shape of the normal distribution depends on 2 parameters, the mean and the standard deviation. And each normally distributed variable has its own particular distribution curve. In other words, height, when you look at the distribution for a population of people and their height, that might be different or would be different than if I looked at distribution for a test I gave or something like that. And you assume a lot of times that tests seem to follow that bell curve standard where you have a few really high, a few really low, and most people kind of in the middle. So when you look at this data here that we've got showing, you've got a blue curve here and you've got a brown curve. And the blue curve is broader, but they both peak at the same place. So that means that their averages or their means are the same. So these means right here are exactly the same for both these curves, but the standard deviations are different. The brown curve is thinner, so it has a smaller standard deviation than the blue curve, which is broader. Here's a couple more examples, another blue and brown curve that are completely different. If you thought of this baseline as a number line, perhaps, then the average or the mean of the blue curve in both instances is very far away from the average of the brown curve or the mean of the brown curve. So you can see that they have different means, both sets of curves. But the top set of curves, B, they're both the same width. They have the same standard deviation, even though they're located in 2 different places. In the C example, the bottom set of curves, you can see that curve 1 is broader than curve 2, which is a little steeper and narrower. So their means are different and their standard deviations are different. So these are properties. Again, these are things I want you to know, so we can put a star there maybe. These are some things I want you to be able to tell me, perhaps on a quiz. Characteristics, or if I might say which is not on a test, which is not a characteristic of the normal distribution. That might be something I want you to know. It's bell-shaped. Excuse me, I'm yawning. Okay, it's bell-shaped. That's important. The mean, median, and mode are equal, so all of those, mean, median, and mode, are located at the center of the distribution, or the peak, the high point of the distribution. The curve is unimodal. That means it just has one peak. It's that middle top is your only peak, so that's one mode, unimodal. It is symmetrical about the mean, which means that if you think of the mean, if you drew a vertical line through the middle at the mean, it has equal parts on each side of it. There's just as much of the curve on the left. It's identical on the left of the mean and on the right of the mean. So the curve is symmetrical about the mean. Also, it's continuous. There's no gaps or holes, so the curve is continuous. You can start at one end and go to the other without picking up your pen. And the curve never touches the x-axis. So no matter how far in either direction you keep extending that curve, it is not going to touch it. It gets closer and closer to it, so close that it might as well be touching, but it's not actually touching. Okay. More properties. The total area under the curve is equal to 1 or 100%. All the data falls under the curve. There's none of it that's outside of the curve. And these are critical numbers that you really need to know. Within 1 standard deviation, 68% of the data falls. Within 2 standard deviations, 95% of the data. And within 3 standard deviations, 99.7, or basically 100% of the data falls within 3 standard deviations of the mean. So if we go through here and look, you can see that from here to here, that's 1 standard deviation away from the mean. 68% of our data falls, and you can see that makes sense because that's the peak. So within 1 standard deviation, we get over half of our data accounted for. If we go out to 2 standard deviations, well, then we're up to 95% of the data at that point, getting almost completely covering the data when we go to 95%, or to 2 standard deviations. And when you go to the 3rd standard deviation out here, you can see that we get 99.7% of the data. So we get very close. And you know that as we go out, because we already said this, as we continue here, if this curve was going to extend farther out here and farther out here, if that curve just kept going, then this data keeps going here too. It keeps getting closer and closer and closer and closer, but never touches. And this keeps flattening out, keeps going and going and going, but again, never touches. So there's still a little bit left out here in these ends that we don't account for. But within 3 standard deviations, we can get virtually all of the information we need. So each distributed variable has its own mean, its own standard deviation. The shape and location of the curves vary, but if we kind of make a standard normal distribution, then we can gather some information based on saying, well, all of them have a mean of 0. Okay, so the standard normal distribution is is a distribution with a mean of 0 and a standard deviation of 1. So this is something also that you need to know about a standard normal distribution curve. Okay. So we're going to go on and talk about the z-value, which is a standard value. This is how the z-value is calculated. we're going to read these z-values from the table, from a table. But if it's not given in the table, you do the value, whatever the data value is, minus the mean divided by the standard deviation. So x minus mu over sigma is how you're going to calculate it. Okay, and I might ask that on a quiz. Okay, so that's something you might want to remember for a quiz. Okay, so here we have the area under the standard normal distribution curve. If it's to the left of the z-value, here's our z-value right here, and to the left of that, and here's a z-value here, it's negative because it's below 0, and to the left of that, well then you can read it straight from the table. Okay, the area given under the curve in the table is what is to the left of the z-value. So that's easy. That one's easy when you can do that. To the right of the z-value is a little trickier. So let's go to the next slide and talk about z-values when we want the area to the right. You see the shaded area here is what we're looking for, and it's to the left. So suppose the shaded area we want is to the right of the z-value. So here we go here, and we want this area to the right in both these instances. Well, then we have a little trickier situation. We have to look up the z-value and then subtract that area from 1. Now, why from 1? Remember, 1 is the area under the whole curve. So all of this from here, from here to here, okay, has an area of 1. And so if we look up the z-value for this part down here, what we can look up is this. That comes from the table, or this here. Okay, that's what you're going to read from the table. So let's write that down so maybe it helps. This is what you get out of the table. Remember, to the left of the curve. This is what we would get out of the table if we look up that negative z-value. So then we subtract it from 1, which is the area of the whole. Okay, and when you look it up and get the subtract this z-value from 1, then you can find the area of this shaded area that's orange that you're looking for the value of. All right, so let's do a few problems. Oh, never mind. If you want to find the difference between two z-values, well, you're going to find this z-value and it'll read to the left. Okay, and then you find this z-value and it also reads to the left. And so when you subtract the two, you get this value in between. Same thing here. Look up this to the left and then this, and what you get out of the table is always to the left. Subtracting gives you the area between the two z-values. So now let's look up a few from the table. This is example 6.1, page 306. And this is a standard normal distribution table. It is in table E, I believe, in your book. And you notice it says Z up here. Okay, so find the one that says Z. You notice here we have to tenths, 0 to 3.9. Yours may just go to 3. That's okay. And then over here you have to hundredths. So what we're going to do, and I'm going to go back and forth between some slides here. When I go forward in this slide, it says we want the area under the curve to the left of Z is 2.06. So here's the Z-score we're looking for. We're looking for 2.06. All right, so I'm going to go back. Here's 2.0, okay, and here's 0.06. And so we're going to go down, okay, we're going to look down here, going down, and we're going to go across here until we find this Z-score. Now this goes to 5 digits. I think yours only goes to 4. 0.9803. And again, that's the area to the left of the Z-score. So when we go back, we see that it is 0.9803 when we have 2.06. So that's how you find these. You go across from one side, down from the other, and you read the area under the curve. That's what that table tells you. Now we're going to do number 6.2 on page 306. This says we want to the right of negative 1.11, but the key is we want to the right, all this to the right. Well, what the table's going to give us is this. Remember, it gives us the area to the left. So let's look that up. We've got to go negative 1.19. So let's go back. And we're going to do negative 1.1 right here and 9 right here. And we're going to go down and across. Okay. And so we can see that this is the value we want right here, 0.1170. Okay? 0.1170. So we're going to go here. And we see that this, remember, this is what we were finding, is 0.1170. The whole area is 1, so we say 1 minus 0.1170 is how we're going to do our calculation. And what that leaves us with then is this area over here. All of the shaded area is 0.8830. Okay, and all of that should add up to be 1. All right, here is section 6.1, example 6.3. We've got a negative and a positive z-score. We've got a negative 1.37 and a 1.68. So I'm going to just go back. I mean, it's going to kind of be jumpy on you for a while, but let's go back to the positive one. And we want 1.68. So here's 1.6 and here's 8. So we're going to go down. And here's 1.68, 0.9535. Okay. So we go forward. Okay. And we see then to the left from here all the way to the end is 0.9535. That's the area under the curve from here all the way this way. And then the negative 1.37, okay, negative 1.37 right here, and that's still on there, but is 0.08534. Okay, so when I go back, okay, oops, I gotta go one more. There we go. Okay, is 0.0853. Was that what I got? Let me go back. Negative 1.37. Yeah, 0.0853. Okay, just wanted to verify. So from here to here, in here is 0.0853. And that's from here left. Okay, so in other words, then when I subtract these two values, I'll get this area in between. So when I subtract them, what happens here, then I find that that area between the two is 0.8682. Okay. Now, this is 6.4. It's a little different. Find the probability that 0 is less than z, which is less than 2.32. Remember, probability also can only adds to be 1. So the value for z, 2.32, which is from here to here all the way is 0.9898. But from here to here, from 0 to the left, is 50% or 0.5. Okay? So to find from here, from 0 to 2.32, we subtract 0.9898 minus 5. And so we find that this area here, under this shaded area of the curve, is 0.4898. And so you can do, it's the same process for finding probability, because just like the normal distribution curve area is 1, that when you take the sum of all the probabilities in a given situation, it's 1. Okay, here's the last example, 6.5, page 309. Another probability. Find the z-value such that the area under the standard normal distribution curve between 0 and the z-value is 0.2123. Okay, well this is a little different. It's saying this area, they give us the area instead of us giving the z-score and finding the area. The z-score is what we're looking for. Okay, so we know that when we read this z-score, it's going to include everything from here to the left, and that's why we add this 0.5, because all this white area here is 0.5, and this z-score includes that. So we have to add 0.5 to the 0.2123 to get the cumulative area that we're going to look up. Right? And then we go back to table E and we look for that. So let's go back to table E, and we want an area, it's going to be a positive z-score, and we want an area of 0.7123. And these are the things you're going to have to think about as you do this. You know, what do I have to add 0.5 to this? Do I not? What is it asking me? The math is not hard, but you know, making sure you're answering the question can be a little tricky. So if we look here, this is your table, and we go in the body of the table to find 0.7123, and then we read to the left, which is 0.5, and read up, which is 0.06, and so the z-value is 0.56. Now if we look, it's harder to find in a whole set of data tables. Let's go way back to this table here, and we are looking for 0.71, in this case 226, because it's the closest one to 0.713, and so there's a lot of data to look at and a lot of numbers to find it. It's not quite as easy as on that one slide, but you still read over to the left and then up to find that it's 0.56. Okay, so that's the end of our presentation for 6.1. I hope this is helpful to you, and if you have any questions, please be sure to let me know.